Okay, in this video we're going to be looking at prototyping algorithms for embedded systems using Visual Studio. And the example that we're going to work through is this calculation of the distance between two GPS coordinates using what's known as the Haversine formula. So I'm using this web page up here, and it gives the Haversine calculation here. It's basically the great circle distance, so as the crow flies, rather than going through the Earth between 2 points. Being, of course, it's spherical. So it's not too complicated, but we'd like to see, have we implemented it correctly, can we debug it, and can we run through a whole lot of tests on the computer before we actually go through and develop microcontroller code for this. So I've started up Visual Studio. I'm using 2012, but 2013 or any later one will be basically the same. New project, and I'm going to go under Visual C++. I'm going to do a Win32 console application. So this is as close as the code that we can get to our microcontroller running on the computer. And now this one's called console application 5 in the default directory. That's fine for my purposes. You might want to put it somewhere that you can obviously find later on. Clicking next, we get to the application wizard. I normally click next here and go empty project. I prefer to have an empty project and then create it as I want. You might like to have precompiled headers and things, but keep it simple with an empty project to begin with. Noting, of course, console application here. Alright, under source files, I'm going to right click and go add new item. And I'm actually not going to create a C++ file because we are developing C code for our microcontrollers. So I'm going to create a .c file. Now Visual Studio will actually interpret based on the file extension and use a different compiler. We'll actually use the C compiler rather than a C++ one. And we can create a basic C program. So we're going to use standard.io.h, noting that the .h include files are for C. And if you use those ones, you're using the C++ ones. So just note the .h ones are for C files. Int main void return 1, and we'll go printf hello world just to make sure everything's working. Now I normally go debug when it loads. Debug start without debugging. Control F5. So Control F5, and if I bring that in here, you can see hello world. So our program's working, and you can see how quick that was to compile and test. And that's the real key to what we're going to be doing here. So if I just bring up the distance calculation again, this is the formula that we're going to be using. Alright, so sine squared, a few trigonometric functions, some square roots and things. So a little bit tricky on a micro, but let's see how it works first on a computer. And that way we can be sure the results we're getting are actually correct. So what I'm going to do is I'm going to create a couple of new things you may not have seen before. First of all, I'm going to create a type definition. Now we may have seen these with structures, but I'm actually going to do this type def to create a new data type. Now this one I'm going to call as a real type. And I'm going to be using that so I can vary whether I'm using single or double precision in my algorithm by only changing the type def rather than having to change double and float all through my code. And I'm going to create my function. Okay, and that one, long one, that two, long two. So I've created my function here, which is what I want to actually implement on the microcontroller, but I'm going to be trying it here first. Noting I'm using this new data type up here. Okay, so at the moment, these are effectively doubles, which we won't have in our micro, but we're using it just now for testing. What I'm going to do now is declare the variables that I'm going to use. I know we need some delta variables and a couple of constants that we're going to be using throughout this code. So I'm just going to be declaring those here. First thing to do is we want to convert from degrees to radians. Now in order to do that, we're going to need pi. Now if we come up to hash include math.h, we can include the math header file, and I know that mpi is the declared math constant for pi. Now on Visual Studio, if we actually open up math.h and have a look down, we'll see actually right at the bottom we have to declare this constant, or this define here, before we can actually use these constants. And there's our pi down there. Alright, so I need to go, before I include it, define use math defines, just like we define the CPU frequency when we're using the delay routines. So implementing this again, let1 is equal to let1 times, now you see mpi there, divided by 180.0. Remember, when we're doing C code, the .0 is important if we're dividing by a number. Correspondingly, long1 is equal to long1 times mpi divided by 180.0, and I'm just going to copy in the corresponding code here, noting that I should have done flat on the first line. Good. So converted from degrees to radians, as our calculation here is everything in radians. We're going to calculate these delta terms, and then we're going to pre-calculate some constants. So I'm going to go my delta terms, dlat is equal to lat2 minus lat1, and dlong is equal to long2 minus long1. And I'm also going to calculate the argument inside this sine term here, so that we don't have to call sine twice. Remember, this is going to go on an embedded system where we can't do, well, we want to avoid as many calculations as we possibly can. Right, so I'm also going to go calculate the sine terms. So S sine of dlat over 2 is equal to sine of dlat divided by 2.0, and sine of dlong over 2 is equal to sine of dlong divided by 2.0. So I've calculated effectively the term inside this term, rather than having to use sine twice as has been done in this example. Right, so we've calculated that, so we can use our sine squared. Right, now we can begin to implement the sine equation, where a is equal to SD lat2, remember we've got sine squared, so times SD lat2 plus cosine of lat1 times cosine of lat2 times SD long 2 times SD long 2. Alright, so just viewing that again. Okay, there's our sine squared term here. Cos latitude 1 times cos latitude 2 times the second sine squared term. Next one we're going to implement is this line here. So C is equal to 2 times a tan 2 of square root of a, comma, square root of 1 minus a. And then I'm going to return the distance, the radius of the Earth in kilometers times c. So there's our equation. That's the entire problem that we've implemented in C. And quite remarkably, the same code will run on the microcontroller, but we'll have a look at that soon. So let's come up here and actually use it. So I'm going to create my prototype for this here, and what I'm going to do is I'm actually going to use something I've done earlier, and I'm going to use the latitude and longitude of Auckland Airport and the latitude and longitude of Christchurch Airport. So I'm calling it in my have assigned distance formula here, lat1 long 1, lat2 long 2, and then I'm going to print it, which is the nice thing about using Visual Studio, to the console so I can actually see what the answer is. Now I know this is somewhere around 745 kilometers. So let's see if we actually get that result. Once again, I'm going debug, start without debugging, or control F5, and there's the distance printed out, 745.639 kilometers. Alright, so straight away I know this is working. I could run a whole lot more tests over it, but let's start the implementation. Now I know in my microcontroller that I'm not going to have double precision. I've only got floating point in single precision, or 32-bit floats. So I'm just going to move this one down here because we're actually going to look at that number again. And I'm going to begin my implementation by changing one thing. Okay, I've changed the type definition from double to float. That means everywhere you see realty now is, if I hold my mouse over it, now a float rather than a double. And let's see what result we get. We're going to get a few warnings, but we are going to notice a small difference. So this top window here is in double, and this one is in single precision. So you see, the last few decimal places we saw some differences there. All right, as expected, double to single precision is going to give you different answers. However, we also see a whole lot of warnings here. All right, and they're basically conversion from double to float, you're going to lose information, as well as truncation. So it's basically saying, are you sure you actually want to be doing this? And yes, that's fine for what we want to be doing. We could get a little bit more specific and declare all of our constants as floats rather than the default double, which I can do up here as well. We're still going to get a truncation warning because we've got too many decimal points on them. We can always use the floating point single precision versions of the functions rather than the double precision, but the compiler is smart enough to work out that if we are supplying a float, then we're going to use the associated floating point version. But we can try this and we see actually the compiler has been smart enough and we've got the same answer anyway. So we're still working within the expected operating limits. So I'm just going to get rid of those F's because I think they get in the way. The compiler knows what we're up to. So leave it doing what we want. Alright, so at this point I'm confident now that our algorithm works both in double and single precision for this particular example. We might want to try a whole lot more of these values before I'd actually be confident, but let's say we're happy with it. And inside Atmel Studio I've just started up a normal GCC C executable project for the 8090 microcontroller, same as we normally do. And I'm going to take, this is what's quite neat, I'm actually going to copy and paste this function, which I've written for a computer in Visual Studio, and I'm going to paste it here. So this is now in our microcontroller. And I'm going to take our couple of defines that we've used. So include the math.h, our function prototype, and our type definition up there. Type defs work fine in microcode as well. And I've now implemented it inside the Atmel Studio microcontroller code. Finally, I'm also going to copy this over. I'm not going to use the printf. Alright, instead I'm going to go float distance equals _, distance, and I'd probably set a breakpoint. If I now build this code, we'll build solution. Okay, we see unused, that's fine, I'm not interested in that. Okay, I could now run this code on my microcontroller, so I could click debug, hit the breakpoint, run it, step over, see what the distance is, check it to see whether it's the same value or very similar. I'd expect very similar to what we got in Visual Studio. Probably not going to be the same. Different compilers with floating point are going to give different results, but it should be within 1 or 2 decimal places, I would have thought, accurate. So that's basically how you can go from prototyping in Visual Studio, where you get the advantage of the console and printf, so you can see the variables. It's a lot easier to debug. Okay, at any point I can set a breakpoint, push F5 to run it. It will compile virtually instantaneously. It's a lot easier for me to see particular values as I'm going through it, for example. So working and developing in Visual Studio to me is a lot easier. Once I'm happy with it, there's nothing stopping me copying that or actually taking this entire file, loading it into, adding it in as a new file here, if, for example, I've developed a new source file rather than a new main function, and actually using it as my microcontroller code as well. Just remember, I cannot test hardware from within Visual Studio. You want to test the SPI port, you're out of luck. You want to try the ADC, it's not going to work. You might be able to do something with a serial port, but it's not going to look anything like microcontroller code. So hardware's out of the story, but software development often works really well inside Visual Studio and then can be ported across to Atmel Studio or whatever compiler you're using.